Hi Chem Peeps. This is video number 3 with examples of drawing Lewis dot diagrams. Let's start with the first example that I have right here. I can see that this is a metal, sodium, with a non-metal. And right away I put this in my homework just to see if my students are paying attention. This is not going to form a VSEPR theory structure or a Lewis dot structure because I have a metal with a non-metal. Therefore, this sodium chloride has an ionic bond and therefore forms a crystal lattice. So this one would not get a shape with a molecule. So I know that was kind of tricky. Let's look at the next one. We have hydrogen peroxide. And I usually tell my students to start out by drawing their Lewis dot structures for each of the atoms that is found in the molecule. So in the previous video, I showed you the trend for the families and the number of valence electrons that they have. So I have 2 oxygens and 2 hydrogens. Now, I always tell my students to put the atom with the most single bonding sites. So oxygen, and there's 2 of them, has 2 bonding sites. So I'm going to line these molecules up with, or these atoms, I'm sorry, up with their bonding sites connecting or pointing towards each other. So you can see that I turned this first one around so that the single sites line up and they can bond. And what that means is that the 2 oxygens are sharing an electron from each other so that they can form a bond. When I started, I had 6 valence electrons around each of the atoms of oxygen, and they each need a bond. 2 bonds actually to get up to 8, and that is the goal. We want 8 valence electrons through bonding. Now hydrogen, that's a tricky one. It only has 1 energy level. It has 1 electron in its valence shell, so it will share and form a bond and get 2 electrons through bonding, and they both will do that, and that's okay because hydrogen with 2 valence electrons is just like helium with 2 valence electrons, and helium is in the noble gas column, and even though there's only 2, it has a full octet. If we count around the atom, we have 1, 2 for each, 1, 2 for each of the hydrogens, so that's okay. And then around the oxygens, I count the 2 in the hydrogen-oxygen bond, so 2, and then 2 here, 2 up here, and 2 in the bond. So this one has 8 valence electrons. Likewise, if I count around this oxygen, I have 2 in this bond, 2 here, 2 here, and 2 in the bond. So there's 8 valence electrons. This shape is kind of an exaggerated bent shape. So it is bent, and the angle between the bonds for a bent shape with 2 unshared pairs of clouds is going to be about 105 degrees. Let's look at the next example. We have iodine. Iodine is a halogen, and they have 7. And we have 2 iodines, both having 7. They each need a bond once to get 8. So I'm going to move this one so that the single bonding site is lined up with the single bonding site of the other iodine. And when we do that, they share and have a covalent bond. The angle between them is 180 degrees, so we're going to say 180 degrees that this is linear. And they all have 8 valence electrons if we count what they're sharing. Let's look at the next one. We have carbon, which has 4 valence electrons, and we have 4 fluorines that have 7. So we're going to put carbon in the center with the most single bonding sites. This is not an electron right there. And then I'm going to line up the fluorines so that their single bonding site lines up with the single bonding site of the carbon. So that's a shared bond. I have another fluorine, and it bonds. And then I have another fluorine, and it bonds. And I have another fluorine, and it bonds. And so with sharing, the carbon has 8, the fluorine has 8, there are 4 bonds, This angle is approximately 109.5 degrees. And you're like, what? It looks flat. It isn't flat. If you build this, it's tetrahedral in shape. And so it almost looks like a pyramid with a spike coming right out of it. Let's look at this last one over here. Over here we have hydrogen. Hydrogen is not writing. Hydrogen with 1, carbon with 4. Oops. With 4. And nitrogen with 5. Okay, now I'm going to have to do some moving around. First of all, carbon has the most bonding sites, so I put it in the center. I am going to bond the hydrogen and the carbon. That's going to make the hydrogen very happy because it'll have a configuration like helium. Now, the carbon and nitrogen can bond, but it's not going to be enough. And how do I know that? Well, if I count the electrons around the carbon, including the ones in the bond, I only have 6. If I count the electrons around the nitrogen, including the bond, I have 6. So both carbon and nitrogen need to bond 2 more times, but there are no more atoms. Therefore, I am going to move these single bonding sites all the way over here like that and form what we call a multiple bond. And so when I move them, it's going to look like this. I'm going to have another one here, and I'm going to have another one here, and this forms what we call a triple bond. And I want to move these electrons. You don't have to, but I like to put them out here because there's repulsion there. This is linear because the bond angle between the bonds is 180 degrees. Now, if we quickly go back through and talk about the polarity of the molecule, in other words, how symmetrical is the electronegativity pull around the atom? Well, when we look here on hydrogen peroxide, we have electrons on this side of the oxygen, and we have bonds here. That is not equal coming from the center. So this would be what we call a polar molecule. Okay? Here we have iodine, and all the iodines have electron clouds around them. It's equal pull from the center, so this is going to be a nonpolar molecule. Here we have carbon with 4 bonds, and the bonds are all the same. They're all fluorine, identical. This is going to be a nonpolar molecule because it's pulling equally in all directions. If hypothetically, I was to change this to, let's say, hydrogen on just one of these bonds, let's just do that for giggles. Let's say I put hydrogen there. It's no longer equal in all directions. If I did that, I had 1 hydrogen and 3 fluorines, this would then become a polar molecule because it's not equal pulling from the center. And then here's our center. We've got nitrogen in this direction, hydrogen in this direction, not equal. They have very different electronegativity, so this would be a polar molecule. Okay, I hope this helps. Find me on Kim's Chem Chats on TikTok and YouTube, and I have one more video with some trigonal molecule shapes. Find me there.